Okay, some trig integrals. I'm going to give you 3 to start with. All right, so the integral for sine, and actually 2 of these we've kind of looked at in our little game show, what's my function. The integral for sine x was negative cosine x plus c, because the derivative of cosine x is negative sine x, so if there's no negative there, our original function must have been negative. The integral for cosine x is sine x, because the derivative of sine x is cosine x. And then the integral for secant squared x is tangent x plus c, because the derivative of tangent x is secant squared x. So there we're just looking at some very, very common ones. In other words, these are the very common derivatives on the left for the functions on the right. So let's look at the first one here. So we have negative 4e to the x minus sine x dx. Right, we can break that up, and we can also factor out the common multiple, the constant multiple there. So I can factor out the negative 4 and leave the e to the x dx minus 6 sine x dx. And so now the integral of e to the x is, of course, e to the x. So I have negative 4 e to the x minus, and then the derivative of, the integral of sine x is cosine x, because the derivative of, the integral of sine x is negative cosine x, right? Because if we take the derivative of cosine x, that would be negative sine x. So the derivative of negative cosine x is going to be sine x. So now we'll just go on the other way. So if we see a sine x, we know it's going to be a negative cosine x plus c. And so now let's just simplify that up. This is not negative 6 minus cosine x. It's negative 6 times negative cosine x. So this is negative 4e to the x plus 6 cosine x plus c. If having a negative to start off with bothers you, you can also write this as 6 cosine x minus 4e to the x plus c, because after all, the order that you add and subtract in does not matter. Okay? I should say the order you add in does not matter. And so if I have a negative 4e to the x plus a 6 cosine x, that's the same as a 6 cosine x plus a negative 4e to the x. Okay? All right, so hopefully this one wasn't so bad. All right, so we didn't go over a cosecant x, or a cosecant theta. So always, no matter what, on these integrals, simplify whenever possible. And when we're dealing with trig functions, sine and cosine are often easier to work with. So I'm going to change that cosecant x there, or cosecant theta. Okay, so cosecant theta is the reciprocal, not inverse, reciprocal of sine theta. So I can replace cosecant theta with a 1 over sine theta. And then I only have one function. Okay? Having one function is better than 2 functions. One type of trig is better than 2 types of trigs. All right, so this one would be 1 plus sine squared theta times 1 over sine theta d theta. And we can simplify that. This reduces. Sine squared theta divided by sine theta. Remember, sine squared theta is the same as sine theta all squared. So you got two sine thetas. This is essentially sine theta times sine theta. So you can cancel out a sine theta. Okay? So now I've only got one sine theta. One sine theta left. So this is the integral of 1 plus sine theta d theta. And so now I've got a simple trig and I've got a simple power rule. Okay? So we've got the derivative of 1 d theta plus, the integral of 1 d theta plus the integral of sine theta d theta. So the integral of 1 d theta is just going to be theta. And the derivative of sine theta is going to be a negative cosine. Plus c. That's it. It wasn't that complicated at all. Matter of fact, we had the integral of sine theta on the last page. It was the same, so it's the same thing, negative cosine theta. You just had to know you have to reduce first, right? And so be thinking you don't want two different trig functions here, you just want one. And you can change cosecant theta into 1 over sine theta, and then just reduce. Now it's nice and easy. All right, so here we have secant x times tangent x plus secant x dx. The first thing you should note is you do not want a product. So simplify products. Okay, I want to simplify that. Right? So now we have secant x tangent x plus, so just distributing the secant x here, secant squared x dx. Now you can take the integral of each one of these. So we take the integral of secant x tangent x and the, dx, plus the integral of secant squared x dx. Now here's one product that is just fine to have, because that is a nice common derivative. That's just a nice common derivative. Whose derivative? So who has a derivative secant x tangent x? If I take the derivative of secant x, its derivative is secant x tangent x. So if I'm going the other way, I'm integrating, I'm just going the other way. So what function has secant x tangent x as its derivative? Well, that's just secant x. So this is secant x. And who has the derivative secant squared x? Well, if I take the derivative of tangent x, that would be secant squared x. So now if I want to know, if I do the opposite, I want to take the integral of secant squared x. It's just who has secant squared x as its derivative? Well, that's tangent x. I must have been talking a long time. Actually, I've been talking about a good 3 hours here. So my voice is starting to go, because this is 3 hours solid of just talking. All right, so when we take the integral of secant x times tangent x plus secant x, its integral is just secant x plus tangent x. Okay? And you can get that by simplifying those products. Multiply. Okay? You can't help but make it better by multiplying here. And we're looking for our common derivatives. So secant x tangent x, that's a common derivative. It's secant x derivative. Secant squared x, that's a common derivative. That's just tangent x's derivative. Oh, and this one's twice. So let's get rid of it. And of course, this is the one we went over earlier. So the antiderivative of an exponential function is just the same function, same thing, divided by natural log of b. Because if we were taking the derivative, we'd multiply. And then plus, of course, our constant of integration. So I think this might be the last one. I am not going to do the very last part. I think I might save that part. Either I'm going to do it tomorrow or I'm going to do it in class. You'll know because you'll either see it tomorrow by the end of the day, and the end of the day means like 6 o'clock, or you won't see it at all. All right, so we have the integral of 2 to the negative 5x dx, and notice that we have an exponential function there. Okay? Not only do we have an exponential function, that's a little bit of a complicated exponential function there. And you know what? I think I want to give you a slightly easier one for this podcast. So let's do this one instead. Okay? So let's do a nice easy one to end off with. What do you think? All right, so let's do five to the x plus 3e to the x dx. Yeah, let's just do that. Let's just end with a nice easy one. What do you say? All right, so let's integrate this one. So we can integrate 5 to the x dx and integrate the nice pretty 3e to the x dx. So our function, and we'll check this one too. So our function that has 5 to the x as its derivative would be 5 to the x natural log of 5 plus, and then the integral of 3e to the x would be 3e to the x plus c. And if we were to take the derivative of 5x natural log of 5 plus the derivative of 3e to the x plus c. So we take the derivative of that. We'd have 5x natural log of 5. Natural log of 5 is just a constant times natural log of 5. Because the derivative of 5 to the x is 5, excuse me, what is 5x? The derivative of 5 to the x is 5 to the x natural log of 5. The divided by natural log of 5 is there, and it's just a constant term. Plus, the derivative of 3e to the x is 3e to the x, and the derivative of the constant, of course, is 0. And that would cancel out, giving us 5 to the x plus 3e to the x, which is exactly what we started off with. Okay? So I'm going to just skip these two for right now. And so let's take a look at finding a particular solution. And I'm going to do this one in the next podcast because this will take me just a little while, and I've been talking for a long while. So I think that's enough for today, and I will see you tomorrow, and I'll do a nice short podcast on finding a particular solution. See you in the next podcast. Bye.